All right, everyone. Thank you for attending the next talk here. We'll let our speaker introduce himself and the topic. Please give your attention.
Hi, I'm Cameron Bieganek, and I'm here to talk about multiple interfaces today, which is a package I've worked on for a while now. So, multiple interfaces provides a way to work with and define interfaces in Julia. You can define an interface as a list of required methods. You can create new interfaces that extend one or more existing interfaces. You can also declare the interfaces that different types implement, and you can also use multiple dispatch on these interfaces and even interface intersections too, which is something that Kobe mentioned in his talk today. And you can do all that with no runtime cost. Okay, so let me talk a little bit about the motivation for this package, why I was motivated to build this package. Let's consider this example of writing a second function, which is to get the second element of a collection. You might want to define two different implementations for this function, one which dispatches on an iterator and one which dispatches on an indexable object. But as you're probably well aware, that can't really be done right now because the iterator interface is informal and it does not have an abstract iterator type. And the same thing goes for indexability. So we could fix this if Julia had abstract multiple inheritance, which is the ability to inherit from more than one abstract type. So in this example here, you can see I have this hypothetical example where we have multiple inheritance. We could define the array type to inherit from both iterator and from abstract array. So now you could send an array type to the second function, and it would dispatch to the iterator abstract type, and then our problem is solved. Here's just kind of another motivational example, which is designing graph types. Designing graph interfaces is challenging because graphs can have a lot of different traits that you want to try to encode in your hierarchy, but that's hard to do with single inheritance. Here's an example where I start out with just a very basic graph type at the top, and inside the boxes there's a list of methods that are associated with each type, or interface if you want to look at it that way. So we've got two types that inherit from graph. We've got an undirected graph type and a directed graph type. They each have their own edges and neighbors methods that are different. But then you also want to be able to address mutability of graphs. So there's a mutable undirected graph type, which inherits from undirected graph. And there's a mutable directed graph type, which inherits from the directed graph type. But unfortunately, as you can see, they have exactly the same interface. They have the same the same list of 4 methods that are required for mutability. So why do we have to repeat that interface across 2 different abstract types? It's not exactly ideal. Okay, so let me go into a little bit about how multiple interfaces is actually used. So you can define an interface with the interface macro. We have an example here on the left where I'm defining 2 different interfaces actually. First, your functions that are in the interface have to actually be defined. Otherwise, you'll get an undefined variable error when you use the interface macro. So first I define the functions A1 and A2, and I define an interface A, which consists of the methods or the functions A1 and A2. And similarly, I define an interface B, which consists just of the method of the function B. And then on the right, we see that you can actually extend existing interfaces, and you can extend more than one. So this is where the multiple inheritance comes into play. This interface C is extending both A and B, and it's adding this function C. The extension is to add the function C to the interface. So extending an interface means that you're basically adding on to existing interfaces. So this diagram on the left kind of diagrammatically shows this multiple inheritance that we've got here. So in order to implement the interface C, you have to also implement interface A and interface B. So I have some just utility functions here that allow you to query what are the required methods of an interface. So the required methods function, as you can see on the right, when you call it on interface C, it just tells you the functions that are declared to be part of the extension, which is interface C, the ones that are explicitly declared in the interface declaration for C. So that's just the function C. But of course, C extends A and B, so in order to actually implement C, you have to implement A1 and A2 and B also. So to get that full list of all the required functions that you need to implement, you can use the all required methods function on this interface C. So it returns the list A1, A2, and B and C. Okay, so now we need a way to declare which types implement which interfaces, and that's what the type macro does. So in this example, I've got 4 different types actually. Ant, bear, cat, and mouse. Ant implements A, bear implements B, cat implements C. And we see here that mouse implements both A and B. So you can provide a list of interfaces that are implemented by this type. One thing to note though is that, so take this example, cat implements C. Remember that C extends A and B. So in order for cat to implement C, it must also implement A and B. So that means that these 2 declarations on the right are actually equivalent. So you can, if you want, you can just use the one on top, cat implements C, and that implies that it also implements A, B, and C. Or you can explicitly list them all out like this on the second example if you want to. They're both equivalent, so it's up to you which one you use. And it turns out to be very useful to define interface intersections. A lot of types implement more than one interface. And so the way that you represent that is with an interface intersection. And we can create interface intersections in this package by using the ampersand operator, the AND operator. And it has some nice properties. It'll automatically simplify the intersections. So like here, if you intersect an interface with itself, of course you just get the original interface. So A and A is just A. A and B can't be simplified. So it's A and B. These are the same interfaces that are defined here. But also the order that you intersect the interfaces doesn't actually matter. So A and B equals B and A, as you would expect. And here's another case that gets simplified. Because C extends A and B, the intersection of A and B and C is just equivalent to just C by itself. So this simplifies to C, and so does this longer version, A and B and C and B and A. That also simplifies to C. Okay, finally, we need to be able to dispatch on these interfaces, and that's what the iDispatch macro does. So you can create methods that dispatch on both types and interfaces. And I call these methods iMethods, which is short for interface dispatch methods. So here on the left, I have an example where I've defined 4 iMethods for the function foo. And you can see they dispatch on both types and interfaces. So you use this colon syntax in order to define a dispatch on an interface. And note in the third method, we've actually got the third argument is dispatching on an interface intersection. And so we've just got some examples on the right of the dispatch in action. You can see in the first 2 examples that the dispatch on types does work as expected in the first argument. And then you can see down here in this example, we use mouse for the third argument, which if you recall, that mouse implements both A and B, so it matches this method here. It's the same as in regular Julia. We pick the most specific matching method. So in this case, for this call here, the most specific matching method is this third method here. And note that in this last example, cat implements C, which is actually more specific than the intersection of A and B, because it adds one additional method. It extends in A and B by adding one additional method, so it's more specific than the intersection of A and B. So this last call dispatches to the last method. Okay, and a lot of people are interested in performance in Julia, so it's important to know that the interface dispatch that this package provides compiles away. So here's just a simple example where we have a type crow that implements Q, and we have two I methods, one that dispatches on P, one that dispatches on Q. On the right, we can see that all of the dispatch infrastructure in multiple interfaces basically just compiles away, and it just returns the integer 2, which is what we expect. I've also got a benchmark here that shows that it's really just returning the integer 2. There's no allocations. It's very fast when you call bar on a crow. Okay, so the reason I implemented this package is because multiple inheritance is a powerful way to express the relationship of various interfaces. It's influenced by other languages that actually have this, like Haskell has type classes, Rust has traits, Java has interfaces, and they all support some version of abstract multiple inheritance among those, among type classes, traits, and interfaces. And here on the right, you can actually see this diagram from Haskell of a very rich hierarchy of type classes in Haskell and what they call the prelude. So it's kind of like core or base Haskell. So in multiple interfaces, actually all the interfaces in the required methods list, they're all required. There are no optional interfaces. But because we have multiple inheritance, we can still express complex combinations of interfaces, complex combinations of selections of the interface methods that we care about by using the multiple inheritance. So we get the nice property that there's no optional methods, which can be kind of a pain in the butt to work or just to understand and work with. So we get the nice property that all the methods are required, but we also get flexibility with multiple inheritance. So there's kind of an open secret of this package. It's not really about interfaces. It's actually an alternative type system with abstract multiple inheritance. So this has a few consequences. It follows kind of the ethos of regular Julia, where the types, the abstract, in this case, abstract types are the interfaces, and multiple interfaces does not do any kind of enforcing or checking of the interfaces. So it kind of takes a traditional Julia approach of relying on doc strings and unit tests to basically define and test an interface. So I recommend, for interface authors to provide some kind of interface unit test suite, possibly with the help of a package like supposition.jl. I should note that there's some things, of course, that multiple interfaces does not support that are supported by the regular type system in Julia. Things like parametric types, there's no unions. Although personally, I think that parametric types shouldn't normally enter into an interface. That's more of an implementation detail. Okay, so I skipped over the section slide. There are probably some people with questions about ambiguities. So ambiguities can happen when you have multiple inheritance. Even when you're just dispatching on a single argument, you can still have an ambiguity. So here's an example of a dispatching on a single argument where we end up with an ambiguity due to multiple inheritance. So in this example here, we've got two interfaces, bar and quux, which each have one method. There's a type cheetah, which implements both of those interfaces. And then we have two I methods for this function ASDF, one which dispatches on bar, one which dispatches on quux. So obviously, if you try to call ASDF on a cheetah, it doesn't really, the package doesn't really know which method to call because it could be either one. There's really no way of knowing. It's ambiguous. So it just throws a ambiguity error. If these methods are within a single package, this is really easy to fix. You can just dispatch on, you can add an extra method which dispatches on the intersection of those two interfaces. Where the problems really arise is if you have different methods from different third-party packages. However, my gut feeling is that it's not going to be as much of an issue as some people might be afraid. And I'll kind of walk through why I think that's the case. So it's helpful to think about two main categories of methods. We got required methods and provided methods. So the required methods are the methods that are required by an interface. So those methods must be implemented in order to implement the interface. And those methods will typically have dozens of implementations all across the ecosystem. And they usually dispatch on concrete types. So they don't have ambiguities because they're dispatching on concrete types. So the other category of methods then is provided methods. These are typically very generic functions that are defined in terms of the required methods in one or more interfaces. So they usually dispatch on abstract types, or in our case, interfaces. But they usually only have a handful of specializations. And oftentimes, those implementations are defined by the function owner. So there's still no issue with ambiguities because there's only a handful of specializations, and most of them are controlled by the owner of that function, of that provided method. And just to elaborate a little bit more on that subject, here's a more specific example. This is sort of hypothetical. It's not, it's inspired by base, but it's not base, I guess. So we have an iterator interface, and we have, the sized iterator interface. I should be extending the iterator interface. That's a typo. So the iterator interface just has the iterate function, and the sized iterator interface extends the iterator interface with the length function. So the iterate function or method and the length function, those are the required methods for those two interfaces. So there's going to be dozens or hundreds of those implementations throughout the ecosystem, but they're usually on concrete types, and that's okay. So that doesn't really cause issues. And here we have a provided method, which is I called it myCollect just to distinguish it from the base collect, but it's basically the collect function. But I've got two different methods. One dispatches on iterator, one dispatches on sized iterator. But this is a provided method. Usually when you implement an interface, you do it because you want to get these provided methods for free. So you're not going to overload myCollect. Like if I define a new iterator, I'm probably not going to overload collect or myCollect. So I, as the creator of the myCollect provided method, I am in control of both of those methods. There's no issues with ambiguities. So hopefully ambiguities will be uncommon. But we won't really know for sure until we have a little bit more real world data. And we have to see how it works out in the ecosystem. If people start to use this, we need to actually see what happens in real life. Okay, let me go over just some kind of example applications of the package. Going back to the graph type example, this is how we could formulate it in multiple interfaces. Here we've got, once again, this sort of root graph interface. We've got an undirected graph interface and a directed graph interface, which extend to the graph interface just like before. But now we have a separate mutable graph interface, which just extends the base graph interface. So we only have one copy of this mutable graph interface, which is nice. Of course, you'll see there's not actually any multiple inheritance in this hierarchy, but the graph types can implement multiple interfaces, so that's sort of where the multiple inheritance comes in. You've essentially got multiple inheritance going from the interfaces to the concrete types. So here we've got an undirected graph type that I've implemented that implements both the undirected graph interface and the mutable graph interface. And I've got a directed graph type that implements the directed graph interface and the mutable graph interface. And then I can define an I method, foo, which dispatches on an intersection. So I can define one method that dispatches on the intersection of undirected graph and mutable graph, and I can define another method that dispatches on the intersection of directed graph and mutable graph. So we've kind of solved the issue with the original graph type hierarchy. This is just a very hypothetical slide. I like to think about potential ways of organizing a hierarchy of collection interfaces with the having the additional help of having multiple inheritance. So this is very, very hypothetical, just a sketch, and it's definitely not consistent with base Julia 1.x. So any suggestions are very welcome, but the basic idea you can see here. At the very top, I've actually got a container interface, which just has the methods ltype and in. Then the iterator interface in this hypothetical sketch actually extends the container interface. I have a separate hasLength interface, and then a collection interface which extends hasLength and iterator, and it also adds this isEmpty method. So this collection interface is really for immutable collections. If you want a mutable collection, you need to add a few more methods to your interface. So you extend collection to mutable collection with some methods to work with mutability like add, remove, and empty. You also might want to add some other things to the collection interface like getIndex. So we have a sequence interface. This is immutable sequence. The sequence interface is for immutable sequences. So if you want a mutable sequence, then you extend that interface even further to the mutable sequence interface, which adds the setIndex, insert, and delete methods. You could also extend collection to a dequeue with push first, pop first, and push and pop. And in this little code box here, you can kind of just see that, a set, like if you implement a set, it's probably going to implement the mutable collection interface. If you implement a tuple, that would be the sequence interface. Of course, if you implement the dequeue, it would implement the dequeue interface. And if you implement a vector similar to what we have in base Julia, that would implement the mutable sequence and the dequeue interfaces. I also have another example up here. Of course, you can create an alias if you want to. You can create an alias to a interface intersection. So I have an alias for iterator and hasLength, which I call sized iterator. This is all just very hypothetical brainstorming. It would be cool if we could have something like this, but it definitely needs a lot of work. And as it's phrased right now, it's not really consistent with 1.x anyways. So that's about it. I think that abstract multiple inheritance is a really powerful tool for expressing interfaces. It could potentially, of course, have some downsides with ambiguities. But we won't really know for sure until, as I said in the talk, I think it won't be as bad as some people are afraid it will be. But we won't really know until we try it out in the ecosystem.
Hi, I really enjoyed the talk. Thank you. Can you talk a little bit more about how iMethod is implemented? In particular, how you would handle a mutual ambiguity between normal dispatch and iMethod dispatch?
Yeah. Let's go back to that slide. Oops. Okay. Well, so first of all, you can't really combine type dispatch and interface dispatch in the same argument. They have to be in separate arguments. So one argument can dispatch on types, another argument can dispatch on interfaces. And then the way that works is that first it actually dispatches on types, and it treats the interface arguments as any. And then it'll dispatch on the interfaces. So that has at least one consequence, which is if you can, I've been pretty careful about overriding methods. So like if you define like a foo of x, which just dispatches on any, and then you define foo of x, which dispatches on an interface A, that second definition will overwrite the first one because a foo of x, which dispatches on any, from the type perspective is equivalent to a dispatching on an any. Foo of x, which dispatches on A, is equivalent to foo of x, which dispatches on any. So it overwrites the previous definition. So I've tried to be careful about that kind of thing.
Hi, thank you very much for the talk. Like, can you go back to the slides 21, please? I have a question. Like, you've been discussing about like inheritance of interfaces, but what about the variables? In that case here, graph define the variable vertices, but then like the sub classes, the subtypes, like they don't have vertices because you cannot inherit variables. And I think this is something like maybe Julia could be, can do better. That you cannot create a subtype that will a substruct that will inherit the struct variables, the parents. In that case, like how can you make these vertices in graph accessible in the subtypes? It's not clear to me.
Sorry, not sure if I totally follow the question, but so these are methods. So the graph is the interface, and then the
Yeah, but vertices, this is a variable, right?
vertices.
Yeah.
It's a required method of the graph interface. So these are interface extensions, which mean that they add on to the interfaces that they extend. So the undirected graph interface includes neighbors and edges plus the method vertices. So if you want to implement an undirected graph, you have to implement a neighbors method, an edges method, and a vertices method.
Yeah. Okay, but I mean, what you're saying is that we could have like efficient multiple interfaces, like useful multiple interfaces, without inheriting variables, and that looks weird to me. I don't know. I would be happy to discuss that further.
Yeah, I'm still not sure I totally understand your question.
Well, I mean, if you have like a point type that has an x and y, and you
Yep.
have a color point that just want to add color to a point.
Yep.
How do you do that if you can't inherit variables?
Well, so there's no concrete inheritance here. Just like in regular Julia, concrete types are final. These are simply interfaces that represent inherited behavior. So each individual graph type is still going to have to implement its own methods. Like, these two graphs down here, my undirected graph and my directed graph, they have totally separate implementations. You have a struct with whatever fields you want, but as long as each of them implements these methods, then you're good.
How, separating from the dispatch between types and interfaces, how does this actually implement interfaces? And how do you do dispatch on those?
How, you mean how does the dispatch work under the hood kind of?
Yeah.
Well,
Enough time.
yeah, it's kind of a long question, but basically, when these various macros are overloading, or they actually redefine some functions which return tuples of singleton types, and those singleton types are used within the dispatch logic. So everything happens basically at the type level, or kind of like that. It's a long question.
We are out of time for questions, but could we have one more round of applause for our speaker?